So I'm going to go over the analysis and redesign of staple gun. This is our final presentation. The first couple slides are all sort of a recap from our intro presentation, so I'll go through pretty quickly. Here's our exploded CAD for our staple gun. Some background information. Our production volume is about 10 to the fifth, 10 to 6 parts per year. Primary customers are hobbyists, with our secondary customers being the construction sector. Our fast diagram is largely the same from the interim report. We did make a couple changes to some of the leaves, which are reflected in some of our other slides upcoming. Function component mapping matrix is very much the same as it was previously, just making sure it's consistent with our fast diagram. The same is true with the function differentiation table, just making sure that our functions match up to what's put on the fast diagram. Component commonality table is also exactly the same. We have the same two modules, which I'll go into right now. So first module is a handle. We decided to make a new longer handle in order to allow the user to do a little more leverage in order to pair with our second module, which is going to be the spring. We're going to keep all the geometry of the spring the same, but use a stiffer material in order to allow more force in order to get the staple to be able to go on some harder materials that the construction worker might face on the job. Because of the way we redesign these parts, the trip crawl, which is the top image, and the head screw subassembly, which is the bottom, can maintain the same geometry and fit between both and work between both of our models. So product family architecture diagram, you can see we've moved the handle and head screw subassembly as late as possible within those assembly steps in order to achieve that delayed differentiation we want. So design for manual assembly part one, sort of the new material. For the first thing we did for the trip crawl is we eliminated the need for rivets. We've now changed to snap fits, and then we've added a ridge to avoid nesting. Up next, we have the driver blade. We actually consolidated the driver blade and the plunger body into one single part. We've added features to facilitate orientation, make it easier for whoever assembling this to put it together. We've also eliminated fasteners. So a quick before and after analysis. Before, we had 3 separate parts, 4 rivets required, about 50 seconds to assemble. Afterwards, we only have 2 parts now, no rivets. It takes about 20 seconds to assemble, but likely a slightly higher manufacturing cost than previous. So now walking through the how to select the manufacturing process. We see for the trip crawl, it's prismatic, non-singular. It's also a metal. We end up going with aluminum, so it's going to be non-ferrous metal. Filter by mass and thickness. You see here listed in the black boxes. And then lastly, sort by economic batch size. Within the black box, we see about the only thing that's viable for this is going to be die casting. So moving on to calculating the cost of die casting. It comes out to about 9 cents per part. So we'll walk through this briefly. Material cost, just based on how much material costs and given the geometry of our part, which is easily obtained through SolidWorks. And we have our machine operating costs. These are all calculations based off the geometry of our part and how many cavities we're going to have into a single die cast mold. We end up selecting the 900 kilonewton die casting machine. Then using this information, you can calculate our cycle time, which comes out to be about 12.17 seconds. And then we also have the trim press and the trim cycle times, which end up, $35 per hour set, ends up taking about 11 seconds.
So moving on to the automated assembly, for part selection, we decided to go with the subassembly of the magazine rails. This consists of the magazine stopper, inner magazine rail, and the outer magazine rail. And the inner magazine rail shares quite a few functions with the other 2 parts, which show good signs of being able to consolidate some of the parts together. So in the old system, there were 3 parts and 3 fasteners. In our newer design, we the outer magazine rail into 1 part. Fastener and 1 other part of the magazine stopper. This helped reduce part count, reduce fastener count, and also reduce part variety. The function doesn't change even despite the design change, and even more beneficial is the fact that the manufacturing cost reduces due to the integrated part, and Based on this, the assembly cost actually goes down from $8.15 to $3.21 with automated assembly. One thing we had to make sure of was that we kept the critical dimension between the walls of the inner rails. We chose 0.5 millimeters based on the variance in thickness of staples to make sure that they were able to still fit and the staple gun was able to perform its function. To decide the machining, we decided to start filtering by material and shape, as you can see in the boxes over here, and then by mass and thickness, and then finally by tolerance and batch size. This brought us to sheet metal forming and conventional machining. We decided to go with sheet metal forming due to it being a cheaper method. So moving on to DfM. So first we start with the cost per part, which was 41 cents, which was based on the material, operation of machinery, and tooling machinery. And then moving on, we have the material cost, which was only 26 cents. And then the sheet metal work cost was around 15 cents, the operating cost. And then we decided to go with this press based on the shearing and bending requirements we needed. And then the cycle time for the press was around 4.8 seconds based on these calculations. And then the die tooling cost was around 0.89 cents. And base cost for profile shearing, and then the based on the redesign from DfM Pro in the first situation before our changes, it was around 25 or 26 cents per part, and then with our changes it went down to 16 cents per part, which was a 38% drop, which is quite nice. This was largely in part due to the change in wall thickness, which went down from 1 millimeter to 0.41 millimeters in thickness, and this brought down the cost by a lot to 10 cents per part. And despite this, we kept the same press for shearing and bending, so those costs stayed the same. For the online quotes based on hubs, the old design came out to around $31 due to having to manufacture 2 separate parts versus the new design, which only cost $26, rounding up. So moving on to the design of product service system, over here, based on our proposed service, the preventative maintenance, calibration, and repair services and supply management choices can be seen over here. And in comparison of the PSS and product-only model, you can see a difference in convenience, reduced downtime, optimized performance, cost effectiveness, and through extended lifespan and reliability. And PS's environmental impact with the service is much better due to the reduces in waste, optimized resource use, enhanced energy efficiency, and the promotion of sustainable practices.